Hello everyone and welcome back to my YouTube channel or the Big Structure Hub. This is the #1 channel for structural insight and a place where you learn, build and innovate. Today I want to start a design of singly and doubly reinforced beam to Eurocode 2. So in this session, you will know how to derive an expression for these two beams, an expression which will be used to design these two beams, that is singly and doubly. So to be specific, you will know how to derive an expression for moment resistance, MR. This is #1. And then #2, you will know how to derive an expression for area of steel in tension. This is #2. And then #3, you will know how to derive the area of steel in compression. Also, you will know how to derive an expression for lever arm, which is Z. So welcome and please stay tuned as I start up to the end. So let us begin by the assumption made when determining the ultimate moment of resistance of concrete cross-section of Eurocode 2. So the assumption made, #1, we have the plane section remain plane. So plane section remain plane. That is assumption #1. Assumption #2, the strain in bonded reinforcement, the strain in bonded reinforcement is the same as that in surrounding concrete. The strain in bonded reinforcement is the same as that in surrounding concrete. That is #2. #3, the tensile strength of concrete is ignored. The tensile strength of concrete is ignored. Then #4, the compressive stresses in the concrete are derived from the parabolic rectangular stress-strain relationship. I think you saw this in my session before this. So I'm very sure you are aware about this one. So the compressive stresses in the concrete are derived from the parabolic rectangular stress-strain relationship. And then #5, the stresses in the reinforcement are derived from design stress-strain diagram for steel reinforcement. Also, I talked about this in my session #4. So you are aware about it. This is figure 3.8 of Eurocode 2. Then #6, the compressive strain in the concrete should not exceed 0.035. Assumptions are similar to those listed in clause 3.4.1 of BS 110 with the possible omission of 0.95D. So the assumptions are the same, but this 0.95D has been omitted on the lever arm, i.e. Z must be less or equal to 0.95D. So let's now go to the diagram that will lead us into the derivation of the equations or formulas for design of singly and doubly reinforced beam to Eurocode 2. The figure below shows the simplified stress block which are used in BS 110 and Eurocode 2 to develop the design equation for bending. So these are the diagrams. So we will develop the design equation for bending from this diagram. So in Eurocode 2, the maximum concrete compressive stress is taken as 0.85 FCK divided by 1.5, whereby 1.5 is the partial safety factor for concrete, and FCK is the compressive stress of concrete. And the depth of compressive block is taken as 0.8x. Is taken as 0.8x. For FCK is less than or equal to 50 Newton per millimeter square, where x is the depth of the neutral axis. X is the depth of the neutral axis. Here it is. The corresponding value in BS 8110 is 0. This is the maximum compressive stress used in BS 8110, and the depth is 0.9x, as shown also in the figure below. So this statement is explaining what is in this diagram. So this diagram is called figure 8.7, singly reinforced section with rectangular stress blocks. And then this is the section of a beam. It's a rectangular beam. And this diagram is for the strain in concrete and the strain in steel. So the strain in concrete, the maximum is supposed to be 0.0035. As you have seen from the statement, is supposed to be 0.0035. And this distance from the top of this compression beam to the neutral axis, this is the neutral axis. Let me name it for you. This is the neutral axis. So this distance is called x from this statement. It is here, where x is the depth of the neutral axis. So this x is the depth of the neutral axis. And remember, this d is the effective depth. D is the effective depth from the top of this beam to the center of this tension bars. And we have this diagram here, which is the stress block in BS 8110. Remember, we are comparing BS 8110 and Eurocode 2. So this stress block is used in BS 8110. And this distance from here up to here is the maximum compressive stress, which is given by this expression, 0.67 FCU over partial safety or factor for concrete, which is 1.5. So if you simplify, you will get 0.45 FCU. So, and this, remember, this is the compressive force, FCC. And this distance from here up to here, I have named it S1 because of space. I have named it as S1, but it's supposed to be S, which is equal to 0.9x. So this distance is S1, which is equal to 0.9x. And this distance from here to where the force is acting is S over 2. And then from here up to here, up where this tension force is what we call Z, or a lever arm. Again, we will come to this stress block, which is used in Eurocode 2. So this stress block, again, this distance from here to here is what we call the maximum compressive stress. So FCD, which is the design compressive stress, is equal to 0.85 FCK over 1.5. Again, this we talked about it in session 4. If you can remember, it is the same thing. And then this distance from here up to here is called S2, which is 0.8x. 0.8x. Here it is 0.8x. Here it is. The compressive block is taken as 0.8x for FCK less than 50 Newton per millimeter square. And this distance from here up to here, up to where this compressive force is S over 2. And then from here up to where the tension force is what we call Z. So this is all about the singly reinforced section with rectangular stress blocks. So these diagrams will help us to come up or to develop equation for bending. Will help us to develop design equation for bending. So let's see how we will develop these equations. So you will allow me to clean here so that we can have space to develop these equations. So I want to begin by 8.8.1. This is singly reinforced beam design. And the first formula to develop will be for the ultimate moment of resistance, which is MRD. So we will use this block for Eurocode 2 and not BS 8110. So we will use this block for Eurocode 2 and not this for BS 8110. So we know that moment of resistance M RD is equal to FCZ. So let me show you on this. So moment of resistance, this is the moment of resistance of concrete. So will be FC, which is this force, as you can see, this force times Z. It is the same as force times perpendicular distance. So FC times perpendicular distance, which is Z. So this one, but FC is equal to 0.85 FCK all over 1.5 times area of corresponding block. But FC is equal to this FCD, which is 0.85 FCK over 1.5 times area of corresponding block. So what is the area of corresponding block? So area of block is equal to, I'm talking about this block. So remember, this is B. This is B. So the area will be B times H from here to here, which is S2. From here to here is S2. So S2 is 0.8x. 0.8x. So this one is equal to 0.8 bx. So this is the area of block. So FC is equal to 0.85 FCK all over 1.5 times area, which is 0.8 bx. We can simplify this. So simplifying this, it means take 0.85, then you divide by 1.5, then you multiply by 0.8. So if we simplify, we get 0.453 FCK bx. And something you should note is that this is equation This is equation. Let me use another pen. This is equation 8.14 of Eurocode. And this one is equation 8.15. Like that. So FC is equal to this one. How about Z? So Z, again Z is equal to, as you can see, Z is this distance from here up to this point. So it means Z is equal to D from here to here. This is D minus from here up to here, which is S over 2. Which is S over 2. From here to here, S over 2. But S over 2 is equal to, as you can see, S2 here is 0.8x. So it's 0.8x. Then you divide by 2. So you'll end up having S over 2 is equal to 0.4x. So which imply Z is equal to, so Z is equal to D minus 0.4x. So we have this expression. So let us call it expression number 1, and this one expression number 2, like that. Again, this is equation 8.16 in Eurocode 2. Equation 8.16 in Eurocode 2. But remember, we have named this equation 1 and this equation 2. This is our naming because we want to combine this one and this one. But to Eurocode, this one is equation 8.16. So allow me to fill in here so that we can continue with this derivation. But remember, this is our basic formula. This is our basic formula, which imply MRD, we will multiply equation 1 times equation 2. So our equation 1 is equals to 0.45 FCK B X, FCK BX, and then you multiply by equation 2, which is D minus 0.4x. So if you open the bracket, we multiply this by this, we will end up having 0.45 FCK BDX. And then this and this minus 0.45 times 0.4. So that is 0.18 x square FCK B. So let's arrange this expression so that you can have an expression which is in order. So this one is equal to 0.45 FCK BDX minus 0.18 FCK B, this is B, then X square 0.45 FCK BDX minus 0.18 FCK BX square. And then from there, I want to give a statement. I want to give you a statement which will summarize this expression. So clause 5.6, clause 5.6.3. So this is clause 5.6.3. It says that this is clause of Eurocode 2. It is a clause for the limit for limiting the depth. So it says that limit the depth of the neutral axis x to, so you limit x to 0.45D for concrete strength class less than or equal to, this is for concrete class less or equal to C50 and C60. So C50 and C60. And 0.35D for concrete classes C55 and 67. And also X is equal to 0.35D to concrete classes less or equal to 55 or 67 and above, and this one and below. So we will limit this X to 0.45D, which implies that we will replace X by 0.5D, because this is for whatever we are doing. Now we are designing, we are developing a formula for concrete class C50 stroke C60. So we will replace X with 0.5D. So hence MRD is equal to 0.45 FCK BD, then X is 0 times 0.45D minus 0.18 FCKB, and then we multiply by times 0.45D. And remember, this is square. So here we will square like that. So we put bracket like that, and then we simplify the expression. Allow me to clean here so that you can simplify our expression. Now, MRD is equal to, we are now simplifying this expression, this one. So 0.45 times 0.45, you will get 0.203, and then 0.203 FCK, then we have B, and then we have D squared, D here 1, D 2. So D times D is D square, minus 0.18 times 0.45 square, you will get 0.0365 FCK FCK B, then D square will be D square. So the final formula will be, now if you can take 0.203 minus 0.0365, you will get 0.167 FCK BD square. So this is the formula for moment of resistance. This is the design formula for moment of resistance. So this is the formula. This is the formula. This is Eurocode 2. And in BS 8110, MU, this is moment of resistance in BS 8110 is equal to 0.156 FCU BD square. So this is for BS 8110. Remember, you are designing as we do the comparison between Eurocode 2 and BS 8110. So this is the formula, and this is the formula used in BS 8110. So we now proceed to the area of tensile steel. So this was number 1. So number 2 will be the area of tensile steel. So we now proceed to the area of tensile steel, which is S1. So we know that this force, which is the tension force, is the one which will be produced by this steel, which is in the tension zone. So remember this area. This is in the tension zone, and this one is in the compression zone. So moment will be given by, moment is equal to Fs, which is this force, times lever arm, which is Z, times Z. But Fs is equal to F is equal to Fyk all over partial safety factor for reinforcing steel, which is equal to 1.15. So this one will be Fyk all over 1.15, like that. So M is equal to Fyk over 1.15 times area of steel in tension times Z, but we want this area of steel in tension. So we can make this the subject of the formula, whereby M is equal to 0.87 Fyk area of steel in tension Z. So to get area of steel in tension, you'll divide both sides by 0.87 Fyk Z. 0.87 Fyk Z. So it means area of steel in tension is equal to M over 0.87 FYKZ. This is the formula used to determine the area of steel in tension. So this is Eurocode 2, like that. So this is equation 8.21 in Eurocode 2. Equation 8.21 in Eurocode 2. Again, you should note that this formula will only apply if MED is less or equal to MRD. So it means the design moment of the beam you are designing must be less or equal to moment resistance, which is 0.167 FCK BD square. So design moment must be less or equal to moment of resistance, which is 0.167 FCK BD square. Let's now proceed to number 3. Remember, this was number 2. So number 3 will be the lever arm, or a Z. How will you arrive on the formulas for lever arm or Z? So allow me to clean here. So number 3 is lever arm or a Z. So M is equal to FCZ, and we can obtain this equation from equation 8.5 from our previous derivation, which we will also obtain this equation, this one, from equation 8.16. Then we will solve for Z. So Z is equal to D into bracket 0.5 plus into bracket 0.25 minus 3 K0 over 3.4 raised to power 0.5. You close the bracket, whereby K is equal to M over FCK BD square. So you can derive this for Z. I have just summarized it for you, but you can take your time and just do the way we did for the moment of resistance. Just follow the procedure and you will arrive on this expression. So this is for Eurocode 2, and it is equation 8.22. If we compare with BS 8110, so this one is for BS 8110, you will end up having this formula. So this formula is for BS 8110, whereby K is equal to M over FCUBD square. So if you take these 3 divided by 3.4 and you round it to 1 decimal place, you will end up having this formula. So the formula remains the same. If you simplify this 3, then you divide by 3.4 and then round it to 1 decimal place, you will have this formula. So the formula remains the same for BS 8110 and Eurocode 2. I'm now done with singly reinforced beam. I now proceed to doubly reinforced beam. 8.8.1.2. This is doubly reinforced beam. So in what case will you design a beam as a doubly reinforced beam? If the design ultimate moment is greater than the ultimate moment of resistance, i.e. MED is greater than MRD, then the compression reinforcement is required. So you will only design a doubly reinforced beam if the design ultimate moment is greater than the ultimate moment of resistance. So this means before you start designing a beam, you have to determine its ultimate or the design ultimate moment. And also you are supposed to determine its ultimate moment of resistance so that they can guide you on whether you'll design a beam as a singly or as a doubly. So the compression reinforcement is required provided that d2 over x is less or equal to 0.38, i.e. compression has yielded, whereby d2 is the depth of compression still from the compression phase. So this is the distance of d2 from the compression phase to the center of this compression reinforcement, and x is equal to d minus z over 0.4. So this is the doubly reinforced section. So this is a section, this is a diagram for strain, and this is a diagram for stress block used in Eurocode 2. So this distance from here to here is b. Then from the top of compression side to the center of the tension reinforcement is what we call d. Remember, this is the tension zone and this is the compression zone. It is divided by this neutral axis. It is divided by neutral axis. So as we have said, from the top compression side to the center of the tension steel is what we call D. And then from the compression side to the center of this tension, or no, compression reinforcement is what we call D2. And then you have the maximum strain in concrete, which is 0.0035. And this is the strain in steel. This is the stress block. We have 0.85 FCK divided by the partial safety factor for concrete, which is 1.5. And this is the tension force produced by these steels. These steels are in tension zone. And then you have another tension force again on the upper sides produced by this reinforcement steel in compression zone. And then you have the compression force as a result of the concrete. And then you have distance Z. So this distance X from here to here is equal to 0.45 D. And then this distance S from here to here is 0.8x. So to determine the area of compression reinforcement, this is the area of compression reinforcement is equal to M minus MRD over 0.87 FYK D minus D2. So this is equation 8.23. And then the formula for area of steel in tension is equal to MRD over 0.87 FYKZ plus area of compression steel. This is equation 8.24. Thereby Z is given by this formula, whereby K0 naught is equal to 0.167. K naught is equal to 0.167. So this is all about a doubly reinforced beam. You can check this formula for BSA 210 and do the comparison. So I leave it that. I leave as an assignment for you. Go and do research on the formulas which are used in a doubly reinforced beam in BSA 210. So that marks the end of today's session. I think it was an interesting session. And in my coming session, we will now start designing doubly and singly reinforced beams. So don't miss the session, because you are supposed to know how you will be applying this formula and how you will be designing beams when given a question or even in the field. So stay tuned for that. And for those who have not subscribed to the channel, please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So we meet again in my next session.